Hello and welcome to today's webinar. Today we will be discussing maximum power point tracking with Fronius inverters. First, I'd like to introduce your team for today. I'm Mohammed Sirat. I'm the Technical Sales Advisor for Fronius for the Southern African region. I'd also like to introduce my colleague Cyprian Okolo, who is the Technical Sales Advisor for Fronius for the Western African region. And I would also like to introduce my colleague David Mwangi, who is the Technical Sales Advisor for Fronius for the Eastern African region. I'd also like to have a look at the different areas that we cover in more detail. So my colleague David, he covers all the markets that are in red. Okay, so that's the vast majority of Eastern, Central, and a bit of Southern Africa. Okay, so if you do reside in one of these countries and would like to speak to a Fronius employee, please do get in touch with David. Then my colleague Cyprian, he takes care of the Western African countries, so those that are indicated in light blue, and those are the English-speaking Western African countries. And then myself, all these green countries are the countries that I do provide support to. I would also like to talk about our distributors for Sub-Saharan Africa. Our distributors offer after-sale services on any products that they do sell to the market. They are also considered as the first line of technical support. They also do keep all replacement parts in stock. And all our Fronius distributors in the Sub-Saharan African region go under what we call Fronius System Partner Plus. Okay. So for example, in South Africa, our distributors are Innomatic Solar and IBC Solar. Then in Namibia, it is Radio Electronics. In Zimbabwe, it's One Stop Solar. In Ghana, it's Tino Solutions. Then in Kenya, it's going to be CAT, GreenSpark, and Knights Energy. Then in Nigeria, it is Components, and Mali, it's Sonikara, and Madagascar, it is Mother Green Power. So again, if you are residing in a specific Sub-Saharan African region and you would like to purchase a Fronius inverter, please make sure that you do contact the right Fronius distributor for your region. We shall have a look at today's agenda. We will first start off with what is a MPPT, okay? After which my colleague will take you through the Fronius Dynamic Peak Manager, which is the Fronius MPPT, okay, that is incorporated as standard in all our inverters. Then my other colleague will then take you through the differences between single and multiple MPPT tracker topology inverters. Okay, we shall have a look at the first question, which is what is MPPT? What does it mean? What does it stand for? The definition for MPPT is indicated over here, which stands for maximum power point tracking. Okay. And what does that mean? On a solar panel, there is one single operating point at any given time where maximum power can be drawn. Okay. We need to try to maintain this point, and hence this is called maximum power point tracking. Okay. An efficient MPPT tracker will always ensure that your panels are always working at their maximum efficiency, no matter what the external conditions are. So the good thing about an MPPT tracker is that it does try and assist you whenever you have a degradation in external conditions, such as maybe there's cloud cover or the load changes, etc. In order to understand how an MPPT tracker works, it's very important to understand how a IV curve looks for a PV panel. Okay, so almost all PV panels on the market have a general IV curve, which is indicated as such below, over here. So what's important to note is that the IV curve for PV cell is probably almost the same as the IV curve for the entire module when you're looking at the general shape of the curve. So if looking at this curve over here, we have current on the y-axis and voltage on the x-axis. What is generally done is that we start off at the ISC, which is your short circuit current. So this occurs when you basically short the two terminals on your PV module. Okay, whenever you do this, you have a voltage level of 0 volts. Okay, however, you have a maximum current level, and this is how on the data sheet of a solar module they specify the short circuit current. Okay, then the next important value to have a look at is your open circuit voltage, which is indicated as VOC. Okay, and your open circuit voltage occurs whenever you open the circuit across your PV panel. So basically, you're not connecting anything across your PV panel. Okay, if you take a voltmeter and measure, obviously under your irradiation levels, you have to have irradiation present for the voltage to be generated. Either way, you will then be able to get your maximum VOC, which stands for voltage for open circuit conditions. Then if you plot the curve, as you can see, this is the general shape of how the IV curve will look. Okay, so you can see it starts with your high current and fairly constant across the voltage range. And at a specific moment in time, all of a sudden there's a drop in current, but we're increasing in voltage. Okay, if you then look at this formula over here, which is power is equal to voltage times current, we can then deduce and draw the power voltage curve over here. Okay, so this blue curve over here is called your PV, which stands for power voltage curve. So as I said earlier on with maximum power point tracking, what are we doing? We're actually tracking the maximum power. Okay, so from this curve over here, we can produce the blue curve, and the MPPT tracker will, throughout the day, always track along this blue curve. Okay, so that's important to note. What's also very important to note is that if we look at what would be the maximum power that can be generated from this IV curve over here, I mean, we can look at different positions in time. So for example, if you look at this point over here, we have a high current, but we have a fairly low voltage. So obviously the power will not be as high as what it could be. Whereas if you look at this point over here, just before it dips, so if you look at this point over here, we can see we have a really high current and we have a really high voltage. And obviously the power over here will be much higher than the power over there. And this is what an MPPT does really well. So if you have an inverter that doesn't have an MPPT, it could give you a power output over here, for example. But an inverter with an MPPT will always try and choose the maximum power point available. So in this example, it would most likely be over here. Okay, and if you translate this IV curve to the power curve, that value over there will be this value over here. Okay. Okay, moving on. How does an MPPT work? So the task of an MPPT is to ensure that the inverter is always operating at the maximum power points. And the MPPT does this by varying the resistance of the inverter input using power electronics. So for example, with a Fronius inverter on the input, we can vary the resistance. And this works in conjunction with our MPPT tracking algorithm. Okay, so for example, I can just indicate it as an image over here. So here we have a PV panel, okay? And across this PV panel, we've got a voltage. And obviously, we also have a current that is being generated, okay? What we can do is with the input resistance, we can vary the input resistance over here. Okay, so you can see this is a variable resistor. When we vary this input resistance, what we basically do is that we can change this voltage level. Okay, and as you saw in the previous slide that I showed you, by changing the voltage level, we can ensure that we can get the maximum power points available. Okay, so this is in a nutshell of what and how an MPPT tracker works. What's very important is that an MPPT is just not only a resistor or a small circuit. The circuit is also controlled by an algorithm. Okay, so with a Fronius inverter, for example, we have what is called the dynamic peak manager, which my colleague will tell you later on. But what the dynamic peak manager is basically an algorithm that will basically control the voltage level of your solar panel in order to ensure that we get and obtain the maximum power points available. Okay, so the reason for this, why we do need an algorithm, is because an IV curve always changes due to irradiation, temperature, etc. And hence the system needs to remember the maximum power point for different curves. Okay, so for example, this is a screenshot of what you will typically find on a PV module datasheet. If you look over here on this left curve over here, and this shows you the IV curve, and you can actually see how the IV curve changes for each set of irradiation values that we're operating at. So for example, if you're operating at 1000 watts per meter squared of irradiation, we can see this, how the IV curve looks in red. Then if for some reason, maybe there's cloud cover, we will maybe drop to 200 watts per meter squared. And all of a sudden from there, we will now be operating at the yellow curve over there. So basically what I'm trying to show you here is that our system needs to deduce between the different irradiation levels in order to ensure that we can always give you the maximum power points available. Okay, but my colleague will go into more in-depth analysis of how exactly we do that. Okay, as you can see, what can also change the IV curve, for example, is your temperature. So what's interesting to note, when irradiation changes, what happens is that the current is greatly affected. The voltage is also affected, but the current is affected much more, to a much higher degree. For example, when we increase the temperature, the current is affected, but not really that much. The voltage is, however, affected much more. Okay, so obviously the different temperatures and different irradiation levels will lead to different maximum power points. Okay, before I hand over to my colleague, I would just like to launch a quick poll. I'd really appreciate if everybody could share their inputs. Okay, so the question is, you should see the question on your screen now. But yeah, the question is, what can you do to ensure your MPPT works at its best ability? Okay, so the first choice is to avoid PV panel mismatching. Okay, second choice, avoid PV panel shading. Third choice is to regularly clean your PV panels. And the last choice is to actively cool the PV panels. So please do select a option, and I will share the results once I have received everybody's inputs. Okay, I shall close the poll in about 5 seconds. Okay, I shall share the results with you. As you can see, the majority of today's audience will avoid PV panel mismatching, and I also agree with that. That is very important. Also, what's also very important is to avoid PV panel shading. Although an MPPT tracker will try to compensate for shading, the output that you will get when you have shading will never be the same than what it was before shading, no matter how good the MPPT tracker is. So that's important to note. And again, we can see a small percentage would also regularly clean your PV panels. Okay, thank you for your input. I now will hand over to my colleague.
All right, so thank you very much, Mo, for the first part of the presentation. So let's continue and look at the dynamic peak manager, which, as my colleague Mo has said, is an algorithm that is embedded in all Fronius inverters. And we are going to continue to look at it by going through again the IV curve. So the IV curve, as my colleague has already explained, is the characteristic curve of a PV of a panel or a module that is showing us at which points we have maximum power. And these maximum power points can also be seen for different conditions. Just to continue from an irradiation perspective, we can have several maximum power points, as we can see highlighted here. So starting from the very highest MPP at 1000 watts per meter squared to the lowest at 2000 watts per meter squared. So our dynamic peak manager that is embedded in all the Fronius inverters is basically trying to track, regardless of the irradiation levels, which is the optimal operating point, and therefore give maximum power to the inverter for conversion to AC. To go further, let's look at the string orientation and how a PV array string is normally configured. So in this case, we are looking at a series connection, and what we know from a series connection is the fact that the total voltage of the string is the sum of all the modules connected in series, and then the current remains constant. So if, for instance, we have 30 volts as the MPP voltage across the panels, then the total voltage, in this case, we are going to have 90 volts as an example. And if we are operating at maybe 9.5 amps per solar panel, then our current level is going to remain current at 9.5 or whatever it is the panel is rated at. So all the Fronius inverters, of course, have the capability to connect the strings directly and to the MPP. And also, just to go further, if depending on the topology that you're doing, which my colleague is going to address later, you can also do a pre-combined configuration whereby you just connect two cables directly to the inverter. But the question we need to answer is what happens in the case of shading. So a normal operating module array or PV array without shading looks like this, and therefore all the panels are getting the same level of irradiation. But in the case that there is shading, something happens, and therefore we have some difficulty at some parts of the array string in terms of pushing current through. So yield losses mostly will come from partial shading, and shading in PV systems should be avoided as much as possible, and you're going to see why. And you can avoid the shading when you are doing the planning of your PV system in terms of the choice of the installation area. However, as we know, there are going to be environmental changes over time that can result in partial shading that was not foreseen. And this could include buildings coming up, building extensions, vegetation, maybe trees growing in the vicinity of the installation, and so on. What we know generally is the fact that shading is going to have a negative impact on your PV system yield, and this consequently affects the projected return on investment period, or the savings that you projected to make out of your system are going to be negatively affected by shading. Therefore, what you need is an intelligent shade management solution to ensure that your system performs optimally regardless of the partial shading conditions. So this optimal performance means therefore that you are operating at the highest maximum power point possible. And therefore the other question we can ask ourselves is that which are the solutions that are available for shade mitigation? At the module level, we have what we refer to as the bypass diodes. And the bypass diodes tries to prevent losses in case of shading, as we can see in this PV string. So we have about 5 modules connected together. And you have a bit of shading on the first module, and therefore the bypass diodes, when the module is shaded, sort of allows that particular module or section of the module to be bypassed, and this happens by the bypass diode becoming conductive. So we can see that the first module is, for instance, operating at about 66% of the potential power output, whereas the unshaded modules are still operating at 100%. The net effect here is that we can have a reduction as well on the voltage level, and therefore, because we saw that the voltage total in a string is the sum total of all the panels connected together, if you are operating before at 150 volts for these 5 panels connected together, then because of this partial shading of one of the modules, we could operate maybe at around 140 or something like this. And therefore, our maximum power point is going to be at a much lower point. The other solution to mitigate shading for modules is what we refer to as DC optimizers. And these DC optimizers are just placed behind the modules, and they operate by adjusting the voltage by either boosting it up or decreasing it. For this to happen, of course, the DC optimizer is going to consume a bit of the energy that the module is going to generate, and therefore that becomes a part of an inefficient setup because you are taking away some of the energy that you have generated before you feed it to the loads. So the more the shade you have, the more the optimizer consumes because it needs to do more work to either boost the voltage up to reach a certain desired MPP voltage. Then in terms of looking at the number of DC optimizers that have been installed, because in this case, for instance, we are looking at each module having one DC optimizer at the back. And therefore, due to the increased number of components, we are also increasing the risk of failure due to the number of components that have been added to the system. Also, another significant risk is MC4 plugs mismatch. And if there is an MC4 plug mismatch, this is also a potential hazard for fires breaking up in your installation. Also, in terms of service, if an optimizer fails, there's a lot more work to be done because you have to sort of dismount the solar module from the mounting structures for you to access the optimizer at the back. And therefore, that brings a lot more service work should an optimizer fail. So looking at this kind of scenario, we see no added economic value by using DC optimizers. And this brings us now squarely to the Fronius Dynamic Peak Manager, which is the embedded MPPT algorithm that we are going to discuss for this session. So as already mentioned, this Dynamic Peak Manager is embedded in all Fronius inverters as standard. And the way they operate is locating the maximum power point at each input voltage. And as we saw, the voltage is going to suffer a bit from both irradiation and temperature variations. And therefore, the Dynamic Peak Manager is going to sort of move across the IV curve and check which is the best operating point as far as the maximum power point is concerned. So this therefore allows faster adoption to changing irradiation levels. And the way the Dynamic Peak Manager does this is to scan the entire IV curve every 5 minutes or so. And once it establishes a new maximum power point, then it compares with the previous maximum power point to check which one has more power and allow the inverter to operate at that point. In case you do not want to have the Dynamic Peak Manager active in your installation or your Fronius inverter, this can be accessed through the basic menu and can be switched off as an option. But the default setting when you get the inverter from the factory is the Dynamic Peak Manager is on. So the Dynamic Peak Manager from Fronius is a highly efficient shadow terror algorithm. And as already mentioned by my colleague Mohammed, the MPPT tracking or MPP tracking is a technique to maximize power extraction from PV modules by checking what is the best operating point as far as the comparison between current and the voltage levels are concerned. Therefore, this algorithm for maximum power point tracking is scanning the IV curve diagram and tries to find this optimal operating point. However, we can look at scenarios that would make the ordinary maximum power point tracking technology problematic. So in the case we have shading, for instance, as we can see in this curve, we have 2 intervals of shade at 9 a.m. and also at 8 in the morning. And these intervals of shade are bringing about 2 possible maximum power points. So if you are just using an ordinary MPPT without dynamism or being able to shift the operating point, then it's going to be stuck at what is referred to as the local maximum power point. So it's not going to find the global maximum power point, at which point the IV curve is giving you a lot more power for the inverter. And the reason for this is that the normal MPPT will just scan a limited area of the IV curve, And by decreasing or increasing the voltage, the operating voltage up and down, the MPPT finds that the maximum power point is reducing, or the power that is coming out of the string is reducing, and therefore shifts back immediately to the local maximum power point. However, the dynamic peak manager works in a very different way. So we still have these three scenarios where at midday we have no shade. So we have a very nice IV curve with a global maximum power point. And then we have another interval at 9 and 8 as well. So the dynamic peak manager in this case will dynamically adapt its behavior when searching for the optimal operating point. It will check the entire IV characteristic curve on a regular basis, as already mentioned. And therefore, because of that, the dynamic peak manager is now going to be able to find what we refer to as the global maximum power point, even in partial shade. So this is going to guarantee more yield and more flexibility. So as you can see, if you're operating at this interval 9 a.m. and you have two possible maximum power points, then the dynamic peak manager is able to know that one of the maximum power points has a higher power output, and therefore is not going to be limited operating at the local maximum power point. So the difference here, you can see that the local maximum power point is probably just about 0.6 kilowatt in output, but the global maximum power point is giving out about 0.8 kilowatts in output. So therefore, that is quite a significant difference in the power outputs for the two operating points. Looking at the dynamic peak manager in practice, we can look at an analysis of a 4 kilowatt residential installation that shows the effect with and without the dynamic peak manager. So as we can see here in this graph, we are looking at two possible levels of operation. So the dark or the black curves represent the operation without the dynamic peak manager, and then the light gray ones represent operation with the dynamic peak manager as an algorithm for maximum power point tracking. So looking at these intervals of operation, we can see that at around 10:30 in the morning, we have a bit of shade. So an inverter that does not have the dynamic peak manager is going to lose quite a bit of power that is possible for generation, even with partial shading, as we have seen the two possible operating points for maximum power in the previous slides. And therefore, the dynamic peak manager in this case is going to guarantee you about 0.3 kilowatts more additional energy for your system. Going further, we look at what are the typical situations that might make the dynamic peak manager from Fronius very effective. As already mentioned, when you're planning your PV installation, you try to avoid shade as much as possible. But then again, because the dynamic peak manager is going to give you a bit of flexibility, you can decide that you're going to have your PV modules as near as possible to roof superstructures if you have your installation on the roof, knowing that the dynamic peak manager is going to be able to mitigate those partial shading conditions. So in this case, we are looking at a daily 1 hour shade, either in the morning or evening from a chimney. And with the dynamic peak manager, you can be guaranteed of 1 to 2% more annual yield out of your system. And then also looking at another scenario whereby you have a dormer extrusion on the roof. So, and this also we are considering 1 hour shade in the morning and evening. And the analysis has shown that with the dynamic peak manager, as opposed to an inverter that doesn't have this algorithm for maximum power point tracking, you can be guaranteed 2 to 4% more annual yield as a yield for your system extra. And therefore, this brings us to the conclusion and the statements that we can make about the Fronius dynamic peak manager. So first of all, the way we can look at the dynamic peak manager is the fact that it's a very efficient algorithm. And this is possible by tracking and detecting any shade conditions and optimizing the yield at the string level. So before the voltage reaches the inverter, the dynamic peak manager has already detected what needs to be the optimal operating point. Also, the dynamic peak manager also offers you safety. because it requires no additional components at the PV module level, as we have seen with the DC optimizers. It is already integrated into the inverter and therefore protected against external influences. And therefore, the likelihood of the Fronius dynamic peak manager failing within the inverter is very, very low as compared to either a DC optimizer on the roof or somewhere else. Also, we can say that the dynamic peak manager also offers you a lot of sustainability because as a shared management solution at the PV module level, when you're looking at the DC optimizers, there is a high risk of failure and therefore greater servicing requirements. But because the dynamic peak manager has everything integrated within the inverter, any servicing that is required will require very minimal effort. And therefore, in terms of sustainability, the dynamic peak manager is going to guarantee you the highest sustainability out of your system possible. So therefore, that brings me to the end of my section, and now I'll be handing over to Cyprian to be able to take you through the remaining bit of the presentation. So Cyprian, if you can take over from here, please.
Yes, indeed, Dave. Thanks for your wonderful presentation. I want to believe that you can see my slide now. So I will be continuing from this point, and we'll be taking on single versus multiple MPPTs, because this has actually been a sort of a point of discussion as to which is best. So here we will be asking the question, which is sufficient for any installation topology that we are dealing with, be it maybe a centralized system or a decentralized system. So, but before I continue, I would love to launch a poll question just before I continue. Great, I want to believe that we can see the poll question now. So the question is, how many MPPTs are ideal in an inverter to guarantee maximum yield for commercial installations or for a commercial installation? So is it 1 MPPT, 2 MPPTs, 3, or more than 10 MPPTs? So feel free to choose your response or select the option that you feel is most correct for you. So it's quite straightforward. So I will be closing the poll question in, say, 10 seconds. I believe that will be enough time for us to respond, and then I will now continue with the presentation. Okay, so I will now close the poll question and then share your responses. Great. So from a response, we have here that 21% went for a single MPPT, 58%, which is the highest, went for double MPPTs. Coincidentally, an equal percentage went for 3 and greater than 10 MPPTs. Great, thank you very much for your responses. We will now continue with the presentation, and then at the end of it, we would now see the characteristics of these or the implication of these using either single or multiple MPPTs for an inverter. So, like the question was asked initially, which is sufficient for installation topology, either for a centralized or decentralized system? Great. Let's now continue by looking at a very, very important factor, which is called mismatching. And then, of course, looking at how we can mitigate mismatching to the barest minimum. By definition, mismatching losses, because it's actually related to losses. Mismatching losses are actually caused by interconnection of solar cells or modules that has different characteristics or specifications, or experience different conditions from one another. I think that's the basic definition. And then looking at IV characteristics at different irradiation levels for modules oriented in the east and in the west orientation. It is discovered that in contrast to large current differences, as can be seen with, of course, the different irradiation levels between the east, the modules installed due east and due west, the MPP voltages are nearly identical, as can be seen also in the graph that is looking at the maximum power point. You can see that it falls within a range, and these range are usually not too far off. So this now means that, as can be seen from the graph, the total voltage of the east due or the due east generator is similar to the total voltage of the due west generator, and then very small mismatching losses are expected if these strings are connected in parallel to a single inverter with one MPP tracker. So that's this was actually an experiment that was conducted, and these are the results that I'm actually sharing. So be it a central topology or decentralized topology, be it if it's a free field, ground mount or rooftop installation, certain points need to be taken into consideration as a design engineer or as an installer to ensure that we provide the best conditions for our inverters to optimally function. That is in regards to MPPT operation. So this basically includes a good orientation of the module, because this is very, very essential, meaning that we would have to work to ensure, or design to ensure that your panels are oriented in a way that would attract the highest irradiation level. That is by properly calculating your solar window, which is usually the sunspot from the highest point or the highest or during the summer when irradiation is highest, and then to the lowest period when irradiation is obtainable. Then afterwards, you can now calculate the proper or the correct azimuth that would give you to ensure that your tilt angle and your azimuth makes your panel oriented such that the sun or the rays of the sun incidence on the solar panel as perpendicularly as possible. So these are the conditions that we need to, as installers and design engineers, take note of to ensure that the solar generators or PV modules trap as much energy from the sun. So coming back to the various orientations that we have, of course, we can have panels due east connected to a particular inverter, and then we also have panels due west also connected to a different inverter, as can be seen in this case. This is for a centralized solution. For a decentralized solution, it's also the same thing. You can have your modules connected. In the previous slide, we had a pre-combined version. Here you have combiner boxes that traps that combines the DC, of course, the power from the modules respectively, combines them, and then goes with a thicker diameter DC cable to the inverter. So for a decentralized version, the modules are connected directly to the inverter. So once this is done, there are conditions, and then there are also arguments asking or saying if this is proper or to have just one inverter handling both east and west orientation of solar modules. So that brings us to the next subtopic that we're going to be discussing. So which is best? Is it east-west generator? That is, in this case, east-west modules connected to one inverter, or different inverters connected or that have solar modules connected to them, one facing east and then the other facing west. So a comparison, which is further on the experiments that were conducted. So a comparison of measured DC voltages with corresponding irradiation and temperature were actually taken for a particular sunny day, and then the results. So this you can, the graphs here shows the result that were obtained. So the installation of a single inverter in an east-west oriented PV system results in a mismatching losses. But then these mismatching losses are, however, minimal and are partially compensated by other positive effects that I will be discussing in the subsequent slide. But looking at the graph, as we can see, it shows here that the DC voltage of the due west generator is relatively higher than that of the solar modules due east, but that is in the morning time. The reverse is the case in the afternoon. So by the time you have a cumulative result, you would have that they tend to complement each other. And then more specifically or more significantly, we can see that the voltage differences are actually very minimal. Same can also be said for the irradiation and the equivalent temperature coefficient, as can be seen. They are quite complementary, as can also be seen from the graph. So taking this comparison onto the power and energy, it can be clearly seen that there is very little difference. In fact, it's almost identical. Because this was an experiment that was extensively done to get precise information, AC power comparison with the corresponding energy yield was also carried out on a sunny day. And then, as can be seen from the results obtainable here, an approximate percentage of 0.1 energy loss was recorded for the east-west generator with a single inverter compared to the east-west generator with separate inverters. So basically, what we are saying is that in terms of cost-saving perspective, and from the graph that we can also see beside here, can be concluded that the cost savings for east-west orientation connected to a single inverter is greater than the energy losses. And then this means that the payback time, or the ROI time, for east-west PV system with a single inverter is shorter, which is now the reason why we call our Tauro Eco. The Eco actually means economical, so it comes or stands out as the most economical design for commercial installations, which makes it very, very competitive in the solar market. So, but there are basic installation rules that have to be adhered to for this to really work out. So the following rules must be observed in order to ensure that east-west oriented PV system with a single inverter operates optimally. So these are, and I believe has also been noted by my colleague Mohammed, shading must be avoided. And then the number of solar modules must be identical in all strings. And then for every string, for each string, the inclination angle and orientation of the solar modules has to be identical. So this conclusively brings me to our Tauro inverter with the cost savings that is obtainable with a single MPP tracker, which is the Tauro Eco. So the Tauro Eco, of course, has a single MPP tracker. This obviously means that only one SPD is required per inverter, because the number of SPD is simply proportional to the number of MPPTs available in the inverter. So if you have multiple MPPTs, it means you're going to need multiple SPDs. And this, of course, with multiple MPPTs, it leads to higher costs of the entire unit. So which makes the Tauro Eco a more economical and the optimal option or choice. And then in terms of the SPDs, we have SPD type 1+2, which are integrated as standard. Although it is understood that for some regions that don't experience, by the way, in definition, SPD type 1 is basically an overvoltage protection, and then SPD type 2 is for lightning arrestor, so which combined gives you overvoltage and then lightning surge protection. So it is understood that there are regions that don't usually experience lightning or very, very minimally. So that is the condition where this device can, the SPD type 2 can be installed as an option. That is only the SPD type 2. Okay, yeah, the definition is reversed, of course. So still continuing as an advantage, the SPDs can actually be exchangeable just in case you have any problem with anyone. You can easily exchange that. So why I'm saying this is that in most cases, competitor SPDs that have multiple SPDs installed with respect to multiple MPPTs, these SPDs are DIL mounted, dual inline mounted, meaning that they are installed in PCB boards. So this implies that if one SPD is problematic, it means that the entire PC board would have to be replaced, which makes it a cumbersome process for servicing. Yes, so having said that, of course, we have 3 major orientations that we can have our solar modules facing, which is the east, west, and of course, due south. So this, of course, is where we now come in with Fronius Tauro, which comes with 3 MPPT trackers, and to address cases where you would need to have your orientations facing in multiple directions. So this comes in very handy to, of course, handle such kind of installation conditions. So in summary, we're not outrightly saying that or condemning multiple MPPTs. We're just giving you facts and figures that buttresses the fact that single MPPT integrated inverters can actually function optimally. But of course, to address cases where we have cases due to shading or irregularities of the installation site, you can of course have this inverter that comes with 3 MPP trackers to address such cases. So to conclude, just like we have in our test site in Castoria, Greece, we can see how the azimuth and the tilt angle of these panels facing in virtually one direction. So with such orientation, it is basically much more economical and optimal to use the Tauro Echo with a single MPPT. So that brings me to the end of my part, but just to add a bit of information for all our installers and partners alike. If you want to get more information, please visit our website, which is www.fronius.com. And more specifically, please, we have, just to know, for you to know that we have 3 business units. Select the solar energy business unit. Go to our information center. There you're going to find our installer support column where you can have access to different documents and support materials that you would need for your everyday function. And then furthermore, you can of course have access to operating and installation instructions also from our website or using this link. And then more specifically, you can have access to all our webinars for the Sub-Saharan Africa region by using this link. So this link just takes you directly to our playlist, Sub-Saharan Africa playlist, where you're going to have a collection of all the webinars that we've conducted. And in case you have any specific topic that you want to have more idea about or just want to have a review of it, you can do so by using this particular link. So in conclusion, if you have further more inquiries to make, you can do so with the respective contact information as can be seen, or more specifically, if you want to contact us, the TSAs, you would have to do so according to the TSA responsible for your region. So with that, we have come to the end of our presentation for today. We hope you all enjoyed it. And yeah, you can stay tuned as we will come by next week with a more interesting topic. So on behalf of my colleagues, I want to say thank you all. We're going to leave the presentation on, say, for about 5 minutes to attend to your questions, and after that, we will call it a day. So thank you very much, and have a wonderful weekend.